When I run into this fire area actor in my level, I take a health damage per second of 4 for 7 seconds. 32 damage because I'm modifying health on application of effect, meaning 1 extra application at the beginning. In my burn damage effect class, I'm applying to health a scalable float magnitude, -1 coefficient for damage, obviously, and I'm using something called a curve table. This curve table has many curves to it, and I've chosen a certain damage curve, which you will see shortly. You can notice we can preview a certain output number for a range of integral values. These integral values in question depict the level of the effect, which can also be a floating number, taking in an interpolated number between the floor and ceiling of this floating number. The same level also applies here for every other curve table in use, meaning for the curve duration in this curve table for a level of 2.5, I will get the number right in between 8 and 6. That is 7 seconds. For the next electric field effect, and please excuse the crappy particle effect being in use, I wish to do a complex calculation for a periodic health damage. I wish to deal a damage per second based on missing health for 5 seconds modified on application. So I take immediate damage when I run into this actor and damage every second. Notice how, in these logs, there is an increasing damage as I lose health, and I've lost up to 132.29 of my health. Likewise, if I run into this electric field once again, I will lose more damage, and after 6 applications, I end up with 18.73 of health. So let me pull out my calculator to verify the difference in health. 200 minus 132.29 equals 67.71. Likewise, 132.29 minus 18.73 equals 113.56. This is like more than 50% increase in damage in the second application. So in the electric field effect, for a duration of 5 seconds, executed on applications, I've modified health using a custom calculation class. I've passed an MMC class, the output value being multiplied by a coefficient of -1 to add as damage. We'll kick things off with curve tables and effect classes. We had created the fire area actor in the matter volume of effect folder, if you remember from an earlier chapter. This actor simply has a box collision and a fire particle system. On begin overlap of the box component, we're just trying to get the ability system component of the overlapping actor and applying the burn damage effect spec. Before which, we're setting a certain fire damage value by a caller tag of this effect spec of a value of -8. Now, in the base ability system effects folder, if you examine the burn damage effect class, we have indeed used setByCallerTag element.fire, so the value of -8 is fetched like a map of values for this effect. Gas provides an option of using a value from a curve table instead. This is because sometimes in most games, you have different values for the same property of an effect. You can choose to get a value of an effect based on the level of the ability or the character or any other entity. Moreover, it's a floating value, not just an integral value, like pressing and holding an attack button to charge your attack and dealing a certain damage value within a range of numbers. This can allow developers to work in a data-driven manner by thinking about systems, balances, and values for various data sources. Let's create the curve table in a model folder inside the effects folder. Model can contain data structures, tables, data models, and other data aspects pertaining to effects. Right-click in this folder, and in the miscellaneous section, you will find the curve table here. You want to choose linear, which helps you plot a linear graph where the data points are connected to each other by a line. And so you have a linear graph which you can visualize later. Let's name this CT burn damage, and within this curve table, you can have a collection of curves here, not just one. You can select a curve table here to visualize and update values, but there are no columns to this curve yet. Let's right-click and rename this to damage by levels, but in GAS, it is known that these curve tables in effects will be used for values by their levels, so you don't really have to name it suffixing by levels or anything like that. Now you can add a new column which will bear an integral value of 1, or if you wish, you can import a CSV or a JSON file stored in your project directory. We will come to this shortly in an upcoming section of this topic. You can choose to have as many columns as you'd like for your game, and for this example, I will set incrementing even numbers, starting with 2 for each level. So back in your burn damage effect class, you can add the newly created curve table here, and you can choose the curves for your curve table, like choosing rows of a data table. And you can also preview the outgoing value for each of the quote-unquote level. Yes, Gas treats these columns as integral level values of the effect. And this does not set the final value of the scalable float, it's just a preview of values of all levels. This number is a coefficient of the outgoing value of this curve at that level, so -1 is going to be multiplied to the value coming from damage by levels at that level in order to deal damage. And like I mentioned, this is just for preview. It is not where you set the values of the final outgoing damage. This level in question must be set at the time of making the outgoing effect spec, for which I will use a value of 2 in order to deal -4 DPS. Let's also check to make sure we have the right duration policy of the effect. Execute on apply for a duration of 4 seconds means 5 executions on health. Let's also make sure to quickly set the stacking policy, aggregate by target, and stack limit of 1 means for the target of the effect, there can be at most 1 active effect. We can also prevent refreshing and repeated application of the effect after the duration by setting this duration refresh policy to never refresh. Let's also go ahead and use the stun gameplay queue now that we have covered the gameplay queues topic. You don't need to provide anything else but the gameplay queue tag. Now, if I walk into this fire area actor, I will be applied the stun gameplay queue. Yes, it is only the queue tag, not the status effect tag, so I'm not blocking movement or ability activation. Likewise, we can add another curve to the same burn damage curve table for duration. By our game design, let's have a decrementing duration values across the levels. And so you can now visualize a curve, a linear graph of the data points of duration. So you can visualize and see where the steepness or the stagnation in values exist. Obviously, for the same delta change in values, you will see a straight line as we did for the damage by levels curve. Back in a burn damage effect, we can choose the same curve table for this duration scalable float value and choose the duration curve. We can now preview the numbers for each level column of the curve table. We can also get a number in between two levels, like I had mentioned. For example, a charged attack or something, where we don't have a fixed integral number for a level. So for the duration curve, let's keep things simple, so that for level 2 of value 8, we can get 9 seconds at 1.5. And consequently, we will get -3 from the damage curve. So in my level, I will take damage on application, and after 9 seconds, this is 10 total executions. I have lost a value of 30, ending with 170 health points. This brings us to the next section, Modifier Magnitude Calculations. Let's work in this section on our matter, volume of effect folders, electric field actor. This too has a box collision overlap volume, as with the fire actor. It has a simple electric sparks particle effect, just to depict an electric field, think about dark clouds and some lightning. In the onBegin overlap event of the box component, we're trying to operate on the overlapping actor, just like the melee operation of combat component that we did. It's literally copy-pasted code from that component's melee operation. And after recording an overlapping actor, if they don't exist in the hit actor array, we're trying to get the ability system component of that overlapping actor and attempting to make and apply an effect spec. A certain duration is set by a caller tag. Let's open up the electric field gameplay effect from the ability system effects folder. Yes, it is the duration effect of a hard-coded value of 5 seconds. It also grants a tag to the target actor element.electric. The only modifier is to add to health, a value of the calculation type, custom calculation class. Yes, Epic Games developers have provided us the option in GAS to perform complex calculations to get the final outgoing value. This could involve complex interactions between tags, other attributes, and many other things, like for example, dealing more health damage to a target with more sources, strength or stamina, or taking reduced damage based on the elemental effectiveness of the target and the caster, like how water beats fire in Pokemon. So, as the name suggests, it is a special class that has a function that executes, which spits out a final value for this magnitude. This magnitude can undergo a couple more operations, like before and after additives, and the whole multiplied by a coefficient factor. Now, from Unreal Engine 5.2 or so, I'm not too sure, there is blueprint support for these Modifier Magnitude Calculation classes, MMCs. So just for demonstration, I will quickly create an MMC in the base folder named BP test. You will notice in this MMC blueprint class, we have only one overridable function, calculate base magnitude, which is of this signature. Yes, for any incoming effect spec, in the end of our custom operation, we just want to return a single float value. Now this can be quite advanced, which we will implement in the next section of this topic. We can actually capture attribute values when this effect spec is created or applied for this calculation operation. We can choose the attributes to capture of the source or target of the effect spec, and if we wish to snapshot that value or not, which we will see shortly. We will learn more about attribute capture definitions, but first, let's do a simple implementation in C++. Create a new C++ class in the Tools menu above and search for class Gameplay Mod Magnitude Calculation. You want to create a new folder in the public ability system called MMC, which is where you can add all of your MMC classes in. Go to the definition of the class Gameplay Mod Magnitude Calculation, and you will notice you have the same blueprint native event declared in the C++ header file calculate base magnitude. So in order to implement this function in C++, in your MMC class, under a public access specifier, paste the same function declaration, but we need to do something different, it being a blueprint native event. In Unreal Engine, we can actually override such blueprint native events even if they are not declared as virtual, thanks to this ufunction macro that takes in a constant value blueprint native event. Epic Games developers have implemented something known as the reflection system. So what happens under the hood is that there will now be such generated header files for your Unreal Engine classes, within which you can find your compiled and built function declarations that the editor and your game will use in runtime. Notice how the generated header file has declared the same blueprint event with the virtual keyword here? That's exactly what reflection system does. It generates these binaries and generated header files that can still be imported and used in your source code. And since they're suffixed with _ implementation in their declaration, we need to do it the exact same way in our C++ source code in order to implement any blueprint event. Oh yeah, it's declared as a const function. I missed that one. And that gets rid of the red squiggles in your editor. Before we continue, let's get a quick understanding of MMCs with this definition flashcard I created. MMCs are technically classes that allow complex calculations for a magnitude in an effect class, which could be periodic or not. They just have one function invoked that returns the outgoing float value. This function provides to developers the effect spec, which the MMC is created for, as an input parameter, so developers can operate based on the source or target's gameplay tags or attributes or other properties. MMCs can run on both server and client and fully support client-side prediction. They also operate with something known as attribute capture definitions that capture attribute values of source or target at the time the effect spec is created or applied. These attribute capture definitions also allow snapshotting or not of the attribute values, meaning snapshotting will use the value at the time of creation of the effect spec by the caster, or no snapshotting means using the current value of the attribute at the time of the calculation. If you remember, I had an analogy for gas. It is a galaxy of interactions, and each actor within an ASC is like an individual solar system. The ASC is at the center of it all, like the star of the system, and it handles coordination between all of the entities, like attributes, effects, queues, abilities. I did forget to mention the last topic. Ability tasks can also be included here, as a moon orbiting the ability planet of the ASC actor. Likewise, the MMCs and ECEs, which is another class you will learn about in the next chapter, can also be thought of as moons to this effect planet of this ASC actor. Technically, they're only ever used by gameplay effects for calculations. MMCs depicted by a white moon here, are networked and hence predicted. ECEs, depicted as a dark gray moon here, are not. Now, as part of the first step in this method's definition, let's attempt to get the source and the target ASC, and please do remember, we're just trying to do the simplest operation first, before we work with capture definitions in the next section. We can get the source and target information from an effect's context. The effect context pretty much holds information of the instigator or the effect caster and the effect target. The effect context data is packaged with source ASC as the original instigator ASC. Yes, I know, it's not named as source. Original instigator is synonymous to source in gas effect contexts. Gas calls this the ASC that started the whole chain of effects. Imagine there is a point A and a point B of an effect application, and they're quite like the source and target of the effect spec, since they are the gameplay conditions where an effect could be mirrored back to the source, or the effect applies more effects due to an overflowing stack. Of course, don't forget to import the ability system component header file in your C++ file, since we are working with the ASC object in this class. And similarly, we can get the target ASC, although this time around, we need to use the getInstigator ability system component. Yes, once again, it is not named as the target ASC. This is like the point B ASC of the effect, so A is the source and B is the target. And so, source is called the original instigator, while target ASC is called the instigator of an effect. So, I want to do a unique calculation here for the electric field effect. I want to damage the target based on their missing health and negated by the magic resist. So, you want to make sure you have initialized your magic resist and armor in your battle attribute set. If you remember, with the init attribute accessor method, just set it to a value of maybe 10. So, a magic resist of 10% means they will take 90% damage. And so, I want to factor in a value of 90% to their missing health as the outgoing damage value. We shall gracefully return 0 if neither ASC is valid or exists. And now, in the second step of this simplest implementation operation, we need to do some untidy things. We need to manually query all that we need, every attribute, certain tags, actors, and other defining values. We're not performing any value captures or snapshotting or caching of any data throughout this operation. So first, let me try to get the current health value of the target ASC. We shall call the target ASC's method getNumericAttribute that returns the current float value of the attribute we passed to it. In order to pass in an attribute, we can include the attribute set class it is defined in, base attribute set class in this case, and call that class's static method getHealthAttribute, which will return that attribute by reference. Think about this like passing the name of your attribute. But gas attributes are not identified by strings, unfortunately, and so this is literally how you pass an attribute by reference in gas and C++. Likewise, we can get the max health from the base attribute sets getMaxHealth attribute accessor method and the magic resistance attribute from the source's ASC's battle attribute set using its getter attribute accessor method. And don't forget to include the battle attribute set header file in the C++ class. Now, the fraction of missing health can be obtained by getting the difference of maximum and current health, although this will be a big number. Imagine a number close to or over 100 for a damage per second. That could be a lot for each periodic tick. And that's why we will work with a fraction of this missing health by dividing this missing health by 10. So now, the resist factor is how much the magic resistance allows. That is, a 10% magic resistance allows 90% damage. So we will subtract magic resist from 100 and divide that by 100 since we are using a percentage for the magic resistance. And finally, the outgoing damage is the simple multiplication of the missing health fraction and magic resist factor, which can be the final return value of this function. And it is also a good practice to use virtual and override keywords in the function declaration and make use of the object-oriented programming inheritance principle. For example, you could have a general MMC that takes care of elemental effectiveness calculations and children MMC classes that perform additional calculations. We can use showDebug ability system in the level to see the attributes of your controlled ASC character. Let's attempt to figure out what our calculated value should be the first second. For max health of 300 and health of 200, the missing health must be 100. Factoring 100 by 10, we are multiplying with 10% of magic resistance allowed damage, so it will be technically 100 by 10, that is 10, times 100 minus 10, the magic resistance, that is 90%, which equals 10 into 0.9, that is 9 damage in the first application. So now, when I run into this actor, yes, in the electric field effect class, we were still using the empty MMC test, which will output 0. Make sure to include the right MMC class, and in your level, press the tilde key for console commands, and press the up arrow for the latest command, show debug ability system. And yes indeed, I did take 9 damage on the first application, and as per our calculations, we're taking more damage each second. Let me pull up my calculator. Notice how we have taken 200 minus 132.29, that is 67.71 damage in the 5 seconds and 6 applications, not 54. And once again, running into this effect will result in a health of 18.73, which by subtracting from 132.29 of health we had gives us 113.56. So yes, we have indeed taken more damage the second time of the effect, since we had more missing health to begin with, losing 113.56 health this time around. And now we can move on to the more complex implementation of the modifier magnitude calculation. Well, up until now, you have been seeing a very poor and inefficient implementation to calculate a value. Like, I know this seems like the right way, you just want to make a simple calculation using attribute values, and you get these attribute values from their ASCs stored in the effect specs context, although there is a much more efficient way to capture these attribute values using something known as attribute capture definitions. These entities define a certain way of capturing attribute values when they are created. Rather than rummaging for values that could update unintentionally during quick operations, we use attribute capture definitions. Let's have a look at the GASDocumentation README file. We just did, as they suggested, implemented their _implementation function that simply returns a float value. MMCs can be implemented in instant or duration effects, and durations could be periodic or infinite. MMCs allow snapshotting of the attribute value to be used during the operation. Think about it to be like a vintage Polaroid camera that gives you a value to work with throughout your operation. For example, if one of your calculation depends on 100% mana, you can snapshot your mana attribute, keeping the full 100%. Throughout the duration of the effect, for each period, your effect will continue to use that 100% of mana of that character, even if other effects modified the mana attribute value to a 70% or a 60%, meaning non-snapshotted value will then work with that diminished mana value for that effect. Let's have a look at their example on a certain poison damage. If the target has more than half the mana or is vulnerable to poison damage, they will take double the damage. When working with attribute capture definitions, we just want to specify the relevant attributes to capture, and in your implementation, you can use this function to get the value of any captured attributes by reference. And then you can simply use those values for your calculations, which in this case is doubling the damage if target has more than half the mana or has a weak to poison status tag. So yes, at the construction level, you will need to specify the relevant attributes to capture like a list. This tells Gas to capture these attributes and optionally snapshot their values when the FX spec is constructed. So let's go ahead and do the same implementation in C++ as in GASDocumentation. First, let's declare the gameplay attribute capture definitions, but even before that, let's pay a visit to their header file and see their definitions. It literally has just 3 properties: the gameplay attribute to capture, the source or tag of the attribute, and if you should snapshot and use a fixed value of that attribute throughout this calculation. So let's name this the health attribute definition. Likewise, we will create another max health attribute definition, and finally the magic resist attribute definition. Let's declare and define the constructor, and for the health attribute definition, let's assign a value for the attribute to capture. And that is done the same way we have been doing, including the classes of the attribute sets. And from the attribute set class, use the attribute accessor method. The attribute source is an enumeration of the type gameplay effect attribute capture source, and we will use the value target. And let's not snapshot the health value since we want to keep calculating with an updating health value to deal more damage. Likewise, we can do the same for the maximum health attribute definition. It shouldn't matter snapshotting or not. Snapshotting will just involve using a fixed value at the time of creating the effect spec. That's it. Similarly, we can use the magic resist attribute of the source with snapshotting to use a fixed value. Now, this is not enough. We need gas to capture these attributes at the time of creating the effect spec. So we have to use this relevant attributes to capture list and add to this list all the attribute capture definitions you have for the MMC. Let's first declare these float values. We also need to declare something known as aggregator evaluate parameters, which you will see shortly. And now it's time for the second most important functionality, get captured attribute magnitude. Observe this function's signature. It returns a boolean indicating whether or not it was ever successful in finding the captured attribute and getting its magnitude. For the first parameter, we'll simply pass in the attribute definition by reference and then the effect spec, followed by the evaluation parameters, just going by the rules and giving it what it asks. And finally, the float value that we need is actually sent by reference. Yes, indeed, returning a negative number or 0 would not work, since they could be meaningful values. Think about this to be like the output pins of the hit result node in blueprints. You could encounter a false value in a situation where, for example, you had a parent MMC class that did the elemental effectiveness check, and in your child class, you assumed a certain attribute has been captured. So that's why such convenience methods exist. Likewise, we can call the getCapturedAttributeMagnitude method again for the max health attribute definition and pass in the float value output that we need, and similarly do the same for the magic resist attribute. And that is it. That's all we need to do to capture attribute values during this calculation. 2 significant steps: relevant attributes to capture list and getCapturedAttributeMagnitude method. And now we can freely perform any calculation we need with the float values we get. That is, the outgoing health damage is now a simple expression. The difference of max health and health factored by 10 and the remaining percentage value the magic resist allows as damage. And that's pretty much it. Just simply return the outgoing damage, build and run your editor. And now, when I test this in the level, we start with 9 damage, and not having snapshotted health means we'll keep operating on the new updating value of health, ending with 132.29, if you remember. The second time, more damage is taken, ending up with health value of 18.73. Now just to show you the other outcome, by snapshotting current health value, notice how we lost 9 health after the first application and 9 onwards, accurately losing 54 health after 5 seconds of the effect, that is 6 applications. The second time, we must lose a different value of health, 300 minus 146, that is 154. Divide that by 10 and multiply that by 0.9, which equals 13.86 health per application. And yes, we actually lost 13.86 times 6, that equals 83.16 value, and we can check that by adding 62.84 current health value to give us the initial value of health. So yes, snapshotting always happens at the time of creating a new effect spec. That is why the MMC operated on the new health value of 146 the second time around. So this is the life cycle of snapshotting in the MMC. The source values are snapshotted at the time of the effect spec creation, whereas the target's values are snapshotted at the time of their first application. Obviously, no snapshotting means using their current running values for calculation. Oh, and also, I forgot to mention, you can also include tags in your evaluation parameters that you can get from the effect spec. So you can set a value to these source tags from the spec's captured source tags, which is actually something known as tag container aggregator. And using its getter method, get aggregated tags, which does return the gameplay tag container. And we can do the same thing for the target tags of the evaluation parameters by getting the tag container aggregator of the target using capture target tags property of the spec. These are actually the tags present in the source or target's ability system components, which are automatically captured by the effect spec so that you can perform your special, unique calculations based on their statuses and other identifying tags. And this brings us to the final section, the assignment. As part of your assignment, I want you to do the same curve table and MMC implementation in the weapon hit effect. In the base, matter, weapon, and sword folder, we have the sword actor blueprint class if you remember. We were doing a simple overlap collision of this weapon capsule volume, and it is a very simple apply effect to self using this effect class in the ability system and effects folder. It is indeed an instant effect, and that's what I want you to do. I want you to use a curve table for this scalable float and choose a curve sword. I've technically imported a CSV with these data values, and you must do the same. This is what the curves look like. You can create this table in Google Sheets, with rows being your curve names and columns being the integral level values. You can name the first cell whatever you'd like and download this as a CSV, and in your Unreal Engine editor, right-click in your folder and in the miscellaneous section, choose a curve table. You must choose linear if you want the values in between and points connecting to form a linear graph. Now you can only ever import this once, so when you click import, it will open up a mini explorer window. Now, I have a folder called dataset, just like the tags folder below, and within this, I have my weapon hit CSV. Select this file, and the table will be imported to your curve table in the editor. So try this first for a scalable float magnitude and a curve, and the next part of your assignment is custom calculation class. You can choose a new MMC class for this effect with a custom formula, coefficient being -1 for damage, of course. And since you know the working of the MMC class, you can go ahead and try doing the same MMC in blueprints. For example, I should place this in the base folder and name this blueprint MMC test2, and we must implement this method calculate base magnitude, which, as in C++, takes in an effect spec and returns a float magnitude. In here, you can use this getCapture attribute magnitude function that will return the float magnitude value of whichever attribute you need. And as in C++, you can specify the relevant attributes to capture right here, which does accept the same three properties as capture definitions do. The attribute to capture, attribute of the source or target, to snapshot this attribute or not. So that's all there is to it in blueprints. Simply pass in the effect spec, and you can also get the effect spec's source and target tags and pass into this method and use the outgoing float value for certain calculations. So why don't you try a formula like this? The effect source does more sword damage with more of their stamina, and the target will take more damage with less stamina. So for a stamina of 75% and more, 3 times damage, and a stamina of over 40% means 2 times the damage. No amplification below 40%. Likewise, for the target, more than 60% stamina means block half the damage. More than 30% stamina, block 25% damage. But in all honesty, such damage negation based on armor and magic resist must happen for every effect and must happen in this post-gameplay effect execute function of the base attribute set where your health resides. You will need the reference of the ASC that owns this base attribute set, get the numeric value of its battle attribute sets, armor or magic resist, and then simply set the value of health attribute directly if you're using health meta. There is also a final lookup curve that gets the value of the level like a scalable float and multiplies it with your outgoing final MMC value, the one after the pre and post additives and the coefficient. So with that, we can conclude this topic. Yes, the MMC was a key part, especially the part where you captured attributes and used their snapshotted or not values. I hope this can help you come up with useful functionalities and features. For example, a Molotov effect that increases burn damage over a duration of time using effect stacks. Thank you for sticking around till chapter 6, and I will be seeing you in the next one.